functions. So what is it? What are the two vector functions that draw those two curves? And you might have a natural question for me like, you know, why? Why in the world would I even care to do that, right? Well, let's say that you own the company that creates these pipe fittings for major cities for their underwater or underground, you know, whatever it is, sewer systems. Maybe it's made out of copper. And you have to weld these things together. You're trying to get some sort of cost analysis, right? You need to know how much weld this is, right? How much weld is that? Well, guess what we're going to be able to do in a little while, a couple of sections from here. If we have a curve living in three-dimensional space, we're actually going to be able to find the arc length of it. We're going to be able to find the length of the curve. So then you'd be able to find how long this is if you took it off the paper and stretched it out, and then you would know how long that bead of weld would have to be, and that's part of your cost. You're going to have to pay someone to do that, right? Materials, labor. And then you can just look at it like, because we can do it. I mean, that's just cool. We can do it. Who cares? We can do it. It's not some mystical thing we can't touch. Right? We can get it. All right, so where are we going to begin with this? All right, where are we going to begin? We don't need the pictures. Tell me about a point that lives on the intersection. Some point that lives on the intersection. I'm just going to call it x naught, y naught, z naught. Tell me about that point. Tell me about it.
On the first one, z is free. Yes,
Are you talking about this one?
Yep.
Yeah. So this point, if this lives on the intersection of both of those cylinders, this point must satisfy that equation, shouldn't it? And it must satisfy this equation simultaneously. Right? That's what we have to have happen? Okay, so let's talk about how are we going to do this. I said we wouldn't need the picture again, but I'm trying to give you a hint here without giving this away. If I turn this and I look at it down the x-axis, okay, which is way out there towards you, right? If I go way out there and you're looking at it, what is that? It's a circle, isn't it? What radius is that? It's the smaller circle, isn't it? So it's a radius of 2. Can you draw me just a circle of radius 2? Can you do that? What would you use to draw that in a vector function? What would you use to draw me a circle of radius 2? 2 cosine t, 2 sine t, right? My question, though, is what plane are we looking at here? Like, what are the two variables here? This way and this way. That's y and z. So you want to draw a circle in the yz plane of radius 2, which means that if I go back here, which of these circles right here had the smaller radius? This one right here? Yeah. Okay, let's draw that. Let's draw that. That alone right there would draw me a circle in the YZ plane, like this, radius 2. Do you agree with that? In the YZ plane, that would draw me a circle. But I don't want my x-coordinate to just be sitting there doing nothing, right? I'll go back to my picture again. See, this was us looking straight on like this on the YZ plane. If I turn it sideways, look at my x-coordinate. My x-coordinate actually changes, doesn't it? Like the x-coordinate, like it's over here, but then it changes, comes this way, and then it goes back, doesn't it? That fluctuation back and forth is what I need to account for. Y'all with me or not? But keeping in mind that I must be on both surfaces at the same time, I must be able to satisfy this equation. And what is it about this equation that you know has to be true? Come back over here. The y must be what? 2 cosine t, right? This is your y, this is your z. Your y must be 2 cosine t? Yes? So if I go back up to this equation right here, and I rewrite it, and I write x squared plus y squared equals 9, if I solve this for x, do you agree I would get that? And you just told me that y had to be what? 2 cosine t, then I could say that the x would have to be plus or minus square root of 9 minus 4 cosine squared t. Do you agree? And that's what this x component needs to be. If the x component is this, then I will live on this cylinder while at the same time living on this cylinder. Do y'all see these two things coming together? These two by themselves make you live on the smaller cylinder, for sure. But the x coordinate or component function being this means you live on the other cylinder. And the only way you can live on both at the same time is if you're their intersection. So let me just rewrite this bigger. So r of t must be equal to plus or minus. That's why we get two functions. I told you we get two functions, right? And then what? 2 cosine t, 2 sine t. We good? We good? Yeah, we're going to talk about domain restriction, but I don't remember that being what I had down here. I think I typed this in wrong. Let's see, hold on. No, I did it a different way. No, it's okay. It'll draw the same thing. What I did, I approached it a little different than I did that one. What I did is I said, well, you have to live on this first. So how would you live on this? Well, to live on that, you have to be 3 cosine t, 3 sine t. And then I said, but then your z has to follow this, and then did the same thing the other way, and I got a different equation. But it should draw the same curves. All right. So what about domain restriction? Do we have any domain restriction here? Do we have some issues?
4 cosine squared t is bigger than 9.
Yeah, could that happen? What about domain? Nothing's going to cause this to go crazy, right? Nothing's going to cause that to go crazy? The only thing that could ever happen is we possibly take the square root of a negative number. So we just need to ask ourselves, is 9 minus 4 cosine squared t, we never want that to be negative, right? So greater than or equal to 0. Is that true or false here? Let's move things over. So I move this over. I divide it through by 4 on both sides. Is this true? Is cosine squared t always less than 9/4? Yes? You could even take the square root on both sides. You get 3/2 less than or equal to cosine t, something like that. Cosine's bounded between -1 and 1, so this isn't. You're never going to have any problems. So our domain here would be what? All real numbers. I'm skeptical. Are you skeptical? I feel skeptical. I did this problem different than I did it in the past, so what I'd like to do is I'd like to open this up and I'd like to see if I can plot that one. So right in here I'm going to plot it, all right? Will y'all give me a moment? Won't take me long. Oh shit, where is it? Okay, it was square root of 9 minus 4 cosine t squared, right? That was the first part. And then cosine t, no, 2 cosine t. Let me delete all this. I'm going to plot this one in, what do you want, green? Moment of truth. Although, I see something's missing here.
I think the inequality is
The what?
the inequality on the board. Because you have a negative 4 cosine squared t.
Mm-hmm. I moved it over and it became positive,
Oh, no.
and then divided by 4.
Okay. I see.
Okay. No, it's all right. It's all right. Let me just try and finish this up here. Okay, that should close that off. That should close that off. Okay. All right, no errors. That's good. Ah, look, there we go. I think I got it. Take them out. Okay, there we go. Do y'all agree that that matched up right on top of the other one? Do y'all see that? I only graphed one of them, though. The other one would be on the other side. Plus or minus. Got it? That's the first time I've ever done that problem that way. I've usually done it the other way, like I showed you over there a second ago, where I restricted on the first cylinder, right, the 3 cosine t sine t. And if you do it that way, the domain restriction's crazy hard. It's. Let me show you what it is. See, what you wind up having to do if you do it this way is you have to restrict this one, which means that, well, I should take a breath here. Do y'all understand what I did doing it this way or not? Yes? You sure? If you go and look at domain restriction here, you have to do 4 minus 9 sine squared t. You need that to be greater than or equal to 0, and when you move that around, that can happen. And then you have to go look at all these different possibilities, and it becomes kind of a pain in the ass. So I kind of like it the way we did it because there wasn't a domain problem. All right, now moving on. Using computers to sketch vector functions is the next topic. And this is just more just so you can see it. All right? Some examples, some cool examples. This is an example of what's called a toroidal spiral. A toroidal spiral. Anybody know what a torus is? A torus? It's a donut, okay? A donut. Oh, a car? Sorry, not. No, a torus. A torus is a donut. So, sacrificial piece of paper. Let's see, anyone have a sacrificial piece of paper? This one. Okay, I got one right here. Imagine if you took this sheet of paper and you connected these two edges together. And this was like really flexible paper. And I take this edge right here and connect it to this edge right here. So I just wrap it around like this. I'd create a donut, wouldn't I? Yes? That's called a torus. And this is a spiral that wraps around the outside of the torus. It's called a toroidal spiral. Got it? Do you see the donut in here? I should have drawn the damn torus in there at the same time. It would have been cool to have it wrapping around it like that, right? That's something I'll do later. But you want to see the vector function for it? Where's the vector function for it? Here it is right here. Highlighted. So the x component is 4 plus sine 20t times cosine t. The y component function is 4 plus sine 2t times sine t. And then the z component is cosine 20t. Now, you wouldn't be expected to like come up with that on your own, but that's what it is. That's what it'll draw it for. All right? That's one example. Here's another example. I'm not going to ask what a trefoil is because someone's going to tell me it's a Girl Scout cookie. Isn't that a Girl Scout cookie? Trefoil? This is a trefoil knot. Okay, so look, this is a curve that draws a knot. So it's very difficult to see it, but this curve knots into itself. I don't know if y'all can tell, but this swings through and goes down on back side, comes back around everything, and then back through behind, and then back through. So it's a knot. If you were to pull it taut, it would be a knot. It would make a knot. And I don't have the code for that one, but I can show you what it is. Here it is up here. Again, you don't need to copy this down. This is just to show you that with computers, we have the ability to draw some really cool curves. Let's see if I have any more. That's it. Derivatives. You thought it would never come. So now we want to take the derivative of a vector function. Well, I've got good news. The derivative of a vector function is just the derivative of the component functions. That's all it is. So now, if when you're taking the derivative of one of your component functions, it winds up having product rule or chain rule or something, then you'll have to do that. But you just do them individually. That's what's great. Now, what is the actual meaning of the derivative, though? So in Cal 1, when we had a function, and I say, hey, everyone, calculus 1, you come to some point here, A, and then I say f prime of A. And what is that? Geometrically, what did that represent? You go up here to your function, you find a point, you draw your tangent line, right? This slope of that line is equal to that, right? That's what it was. See, but now we're in 2 or 3 dimensional space, and the question is, what does this derivative represent? So if you have a vector function, the derivative is a new vector function, all right? And for a given value of t, the derivative would represent a vector which is tangent to the curve at the point on the vector curve. So I have a picture for you. I thought I had a picture. Well, you know what? We're going to look at the picture after we do the mechanical part of it. Let's just see how easy it is to take derivative of a vector function first. So find the derivative of this. Oh, that's a cool vector function. R of t is the vector function t sine t, t cosine t. Any ideas of what that would look like? If this were just sine and this were just cosine, what do you think it would draw? Should draw a circle again, right? It's going to start at a different place, though. Instead of drawing this two-dimensional, instead of starting here and going like this and drawing circles over and over, it's going to start somewhere else. Where would it start? Again, I'm asking you to ignore this for now. If t was 0, where would you be? If t is 0 right here, where would you be? 0, 1, you'd be here, right? And then if you continue, let's see. Let's plug another value of t that you know. That's a very common one. Pi. So if t is pi, where would you be? Sine of pi is 0. Cosine of pi is
They're negative
negative 1. So now you're here. But how'd you get there? Did you come this way or this way? So how about pi over 2? If t were pi over 2, where would you be? Sine of pi over 2?
So 1, 0.
Here. And then, so it's actually drawing it like this way. But starting here. Y'all see it? Instead of doing it this way? Okay, but what you need to realize is that this is going to draw a circle. Regardless of, it's going to be a different direction. Do y'all see that or not? Okay, now, but that's not the problem. It's t sine t, t cosine t. How does that affect things? What do y'all think? If this was 2, 2, what would happen? Be a bigger circle, right? If this were 1/2, 1/2, what would it be? Smaller circle. So do you agree that the number out front has always been like the radius of the circle? But now the radius is a variable. And if we start t at 0, what's going to happen? When we start trying to draw this, it's going to be at the origin, isn't it? It's going to start drawing a circle with bigger and bigger radius. So it's going to try and do this, right? But it has to start here. And then it starts trying to draw, and the radius gets bigger and 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 bigger. And so you get a spiral. Do you all see that? Now, I didn't ask you to graph it. I just asked you for the derivative. So let's see. Find the derivative of it. So what's the derivative, everyone? Derivative of that vector function is, what's the derivative of t sine t? Sine t plus t cosine t? Very good. Product rule. What's derivative of t cosine t? Cosine t minus t sine t? Product rule on this one. We good? That's it. That's the derivative of the vector function. So if you know Cal 1 how to take derivatives, you're in business here. You are in business. If you forgot the product rule, then you've got some work to do. All right, find the vector tangent to this curve at the value of t equals pi over 2. Just plug pi over 2 into this, right? R prime of pi over 2 equals, what is sine of pi over 2? 1 plus pi over 2 times what's cosine of pi over 2? 0, so that doesn't matter. Cosine of pi over 2 is 0 minus pi over 2 times sine of pi over 2, which you just told me was 1. So the vector is the vector 1, negative pi over 2. We good? That's the vector. Questions? Sure? Okay. Now I'm going to show you the picture, and then we're going to answer this last part. We have the blue curve, which was us trying to draw the circle with a variable radius, so it's getting bigger and bigger. I don't know why I only went out that far. I should have drawn more. May I erase? Okay. So we went out and when we draw this, I'm just going to press play. The red vector is the derivative vector. So it gives us a vector that is tangent to the blue curve. You all see it? And what we wanted to do was go to pi over 2, which pi divided by 2, right there. And I asked you to find this red vector. And you told me that vector was the vector 1, negative pi over 2, right? So let's just check it. If I were to go out 1, like I'm going to start at the origin. I'm going to go out to the right 1 and down pi over 2. What's pi over 2? So what's 3.14? Do it on your calculator real quick. What's 3.14 divided by 2? 1.6-ish? 1.5. So here's negative 5. So somewhere around here. I think it's about right here. If I draw this vector, that's this right here. Now, if I just slide it over, because I can do that with vectors, right? It's this right here. Okay, so we have found the vector that is tangent to this blue curve. Do you all agree that that looks tangent to you? All right. Already, do you see the advantage of this versus Cal 1? Look at this right here. Right there at the origin, this red vector right here looks like the vector what to you? What vector does that look like to you? J, 0, 1, right? Yes? In Cal 1, could you have done that? What would the slope of that line have been? Undefined. Already we have something more powerful than we did in Cal 1, because we can actually define a slope, a tangent, at a place that we used to not be able to. Right? Okay, so we found this pi over 2. Now let's go back and look at the last thing that was asked. Here's where we were. We were asked at the very end here, find the vector equation of the line that is tangent to this curve at that point, or at that point in time. So now what they want is not just that vector, but they want the vector equation of this line. Well, they want the vector equation of a line. So what do you need for the vector equation of a line? A point and a direction vector. Which do we have? What's that? Is that our point? Is that our direction? Which one is it? That's the direction. That's V. Look, isn't this red vector right here the direction we're pointing? And then the point would actually be corresponding to the vector from the origin to here, wouldn't it? Which would be the vector given to you by taking pi over 2 and plugging it into just the original vector function. And that'll give you the point that you're at. Understand? So we need to get r of pi over 2. So go back and look at the definition of r. r of pi over 2 should be pi over 2 t times, what was it, sine? T sine t, and then t cosine t. This one's gone? No, wait, sorry. This one's gone, right? Because cosine of pi over 2 is 0. And this is what? Pi over 2? So this vector right here is r naught, isn't it? So the vector equation of this line, which I'm not going to call r. Why am I not going to call it r? Because r is already the blue curve, right? I can't call this line r also. So I'll call it s of t. S of t will be this vector r naught plus t times our direction vector, which was 1, negative pi over 2. And then you can put those together, right? I'll do it. It'll be pi over 2 plus t, and then minus pi over 2t. This is s of t. How y'all feel about this? Somebody gives you a vector curve, vector function. We can now go to any point on that vector function. We can find the vector equation of the line that is tangent to that vector function at any point, so long as we can take the derivative and plug in some values. Good? Okay. We got about 10 more minutes. I don't know how much more I have in notes, so let's just see what's next. Unit tangent vectors. So remember when we were talking about vectors a couple of weeks ago, when we first started talking about vectors, we said if somebody gives you a vector, you can always find a vector that points in the same direction that has unit length. And all you had to do that was to take this vector and divide it by its own length. That's how we found unit vector, pointing in the same direction. Later on, it becomes useful for us to not care about the actual vector itself that's tangent to the curve. That all we look at is what we call the unit tangent vector, which would be a vector that is the same as the tangent vector, but length 1. So here I have the picture of the same vector we just had, the red one. The red one, notice how the length of red is changing throughout the entire process here. But if I don't care about the length of it, and all I care about is the direction, then the purple vector, which is this one right here, is always pointed in the same direction. It's just always has length 1. That's called the unit tangent vector. And we just need to know how to calculate it. It's pretty simple. All you have to do is take the derivative, right, which is a vector, and divide it by its own length. So what would capital T of pi over 2 be for this vector function? Notice it's the same vector function we just worked with. So capital T of pi over 2 will be equal to the derivative of the vector function of pi over 2 divided by its own length. I don't remember what it was. Yes, I do. Hold on. It was 1 negative pi over 2. Wasn't that our derivative? That was our derivative, pi over 2?
Yes.
And then I'm going to divide that by the square root of each of the components squared. So 1 plus pi squared over 4. Isn't that the length of this vector? And then if you write it all as one vector, it's 1 over square root of 1 plus pi squared over 4, and then negative pi over 2 square roots of 1 plus pi squared over 4 again. So I just took each of these components and divided it by this number, and that's your unit tangent vector right there. Like I said, later on it'll become useful. Because what we'll do later is we'll be interested in a different vector that we haven't even talked about yet. This is like when we deal with what's called flux. So we'll have some sort of what we call a vector field. You can think of it as like gravity. Like we're sitting here in three-dimensional space and we've got this force pulling on us. That's a vector. And then we're trying to move in a direction, but we got this force pulling on us. And to get our heads around all that stuff, what we'll do is instead of looking at the vectors, we'll look at the projections of vectors onto tangent vectors. It's just a little easier for us later to work with it. So just want to make sure we know how to compute it. Any questions? We're good? This is an example of a three-dimensional one. See how much more I have in these notes. Man, geez. Okay, I'm gonna leave this for you. Okay, I'm gonna leave this one for you to do on your own. It says for you to find the vector equation of the tangent line to this three-dimensional curve, but there's something missing in here that I haven't given you. It's very important. Like I give you the vector function, right? I want you to find the vector equation of the line that's tangent at this point. So there's some curve sitting out here. You know, it's doing something, and then at some point, that point 0, 1, pi over 2, you're supposed to tell me what the vector equation of the line is that's running tangent to that. In the previous problem, what was it that I gave you that allowed us to figure out all those answers? Well, we took the derivative. That was the vector function. We had that, but there was something else. I gave you t was pi over 2, right?
Yeah.
I gave you the time. This isn't giving you the time, it's giving you the point, right? If I give you a point on a vector curve, can you tell me what point in time it happened? You would have to resolve that t, wouldn't you? Can anyone tell me by looking at this what the t would be in this problem? Pi over 2. How'd you get that? Because z is t is pi over 2 is obvious right there, right? Also, sine of pi over 2 is what? 1, and then cosine of pi over 2 is 0. So whatever your t is, it has to satisfy all these three at the same time. But this one is like given to you. It's a gimme. You see that? So you have to get what t is, and then you can go figure out all the other information, right? All right. I'm going to leave that to you. Second derivatives. Boy, we're moving through Cal 1 fast, aren't we? First derivative, second derivative. So do you remember what the second derivative was in Cal 1? Inflection points. Remember that had something to do with that? Right. Acceleration had to do something to do with acceleration. All right. Well, all we're going to talk about right now is that the second derivative is just the derivative of the first derivative, right? Okay. Now, what is a smooth vector function? Now, there is not something like this in Cal 1. This is where vector functions are going to separate themselves a little bit from what we saw in Cal 1. A smooth vector function. A vector function r of t given on some interval I is called smooth. If the derivative is continuous, that means it exists on I, and the first derivative is not zero, except possibly at the endpoints. What? So look, going back to Cal 1, would you consider this to be, if I took a parabola and let's say this is 2 and this is 10, and let's cut this parabola off, would you say in Cal 1 that's a smooth function?
Yes.
In Cal 1, yes? You'd say that's smooth, right? But notice right here, at some point in here, that the derivative is 0, right? In vector functions, if your derivative is 0, it's not smooth. You can't have a 0 derivative. Do y'all see what I'm saying or not? In order to be smooth, your derivative must be continuous and your derivative can't be 0. So in Cal 1, this wouldn't have worked. We wouldn't consider that smooth in this class. So let me give you an example. Smooth functions. Is this function smooth on the entire number line for every t? So first we're going to do this. We're going to take the derivative. We're going to ask ourselves if the derivative is continuous. So what is the derivative of cosine squared t? Negative 2 cosine t sine t. I can simplify that even more. 4t cubed, right? That's it. That's the derivative. Go back here. I just noticed this typo here. This is supposed to be the 0 vector. The derivative cannot be the 0 vector. Pardon. So is this right here continuous? So is r prime of t continuous? Well, is it defined on all the values of t that we're trying to plug in? You try and plug in t's here. Are you ever going to have any problems? No? How about t's in here? Any problems? No. So, yeah, it's continuous. Sure. But now what we need to check is this. Is r prime of t not equal to 0, except at the endpoints? Well, do I have endpoints? Is t on an interval? No, so I don't even need to consider this. I basically need to make sure that that derivative is never 0. Is that derivative ever the zero vector, damn it? Is that right here ever the 0 vector? Is there a value of t that I could plug in that would spit out the 0 vector? How about 0? What's r prime of 0? You get, well, sine of 0 is 0, right? So that's killed off. And then here you get 0, and that's the 0 vector, isn't it? Yeah, there's a point in there where you have a 0, right? So it's not smooth. It's not. Let's look at the graph, and I think you'll see why. There's the graph. Oh. Okay, let me slow it down a little bit. All right, so time, look at t equals 0. Here's negative. Here we're getting closer to 0, right? About there. Well, something really crazy just happened. You can see it in the picture, can't you? It's like a cusp. But look at your tangent vector. It's going like this, and all of a sudden, boom, it's flipped the other way. Do you see that? So your tangent vector goes from something pointing in this direction, and instantaneously, right from there, it's like this. In Cal 1, it was this issue when we had a cusp. We would say the derivative didn't exist there in Cal 1 because we'd have a positive tangent line, and all of a sudden, bah, it'd flip. We also had this happen on corners, didn't we? This is what it's like for us in vector functions. We get something like this. And that happens when our derivative is 0. Kind of interesting. Vector function. The derivative of the vector function is 0. 0 vector. Thank you. Keep saying that. All right. Oh, I'm out of time. Boy, we were supposed to start 10:08 today. It's okay. Hey, a quick thing on the take-home tests. All right. First thing it says here, due at the beginning of class. That means when class starts, this is due. If you don't turn this in when it's due, if you come in late to class, then you need to have sent me an email, texted me, something. I'm running late. Here's the reason why. You're in the lab. You're getting help. You take an extra 15 minutes to get a problem done that someone else didn't do. That's not fair. Now, I'm not saying that's what you would be doing, but I think it's fair if we have a deadline, everyone's got to turn in at the same time. Because I've had students before, they just don't come to class because they would rather go to do the test, and at the end of class, they come in. I will not accept that. So there will be penalties if you turn it in late. Understood? Yes? Okay. If you did not turn in the test, make sure that you talk to me. Stay after class. Let me turn off my recorder. You can start your homework from 10:07. I don't think you can do it all, but you can start it.